Hello everyone, we are group 79 and our project is titled Predicting House Prices Using Neural Network. I'm Nhật and I'm presenting today along with Jay and Alex. Before jumping into the technical detail, we want to explain the motivation behind our project. Predicting housing price is a critical task for both homeowner and real estate professional, but it's also very challenging. It's time-consuming and prone to human error. Our project main objective is to automate this process using a neural network. The goal is to make housing price prediction faster, more consistent, and ultimately more helpful for decision making in real estate market. Here is the dataset we use for our project. It comes from Kaggle House Price Prediction and contains 80 columns covering everything from lot size to zoning type to number of rooms. Some features are numerical like square footage or year bill, while others are categorical like the type of street or zoning classification. Here are the input and output used in our model. We selected 22 input features that are most relevant to house prices. We group them into categories like lot characteristic, house feature, basement feature, to reflect the different aspects that contribute to home value. On the output side, we are predicting just one thing, the sale price of the house. That's the value our neural network try to estimate even on the input feature.
In our project, we began by selecting a diverse set of baseline models to evaluate the performance of our data. These models include linear regression, decision tree, SVM, a two-layer neural network, and gradient boosting. We chose these methods because they provide a comprehensive understanding of different approaches and serve as different benchmarks for a model. To evaluate performance, we chose 4 key metrics: root mean squared error, k-fold cross-validation, median absolute error, and finally, the RMSE divided by the mean price, which helps put this error to put into like a perspective of average home prices. For a more advanced approach, we turned to the MLP, a deep learning model, and we used a deep learning model with 14 hidden layers to capture complex nonlinear patterns in the data. The architecture of this MLP is particularly deep, with hidden layers shown as is. We ended up with these many smaller layers because we originally started out with several large layers, but that ended up overfitting and overtraining significantly. We arrived with this implementation and these exact numbers by doing hyperparameter tuning, and after a while, this is what we ended up with. We use the ReLU activation function throughout to help introduce nonlinearity and alleviate the vanishing gradient problem, along with the more efficient tuning. To optimize this network, we selected LBFGS, although normally we'd go with Atom, but the data set was particularly small, and LBFGS is good with smaller data sets, while Atom's better with largers, is what we found. And the optimizer we chose is particularly effective with a large number of parameters, like our project. To prevent overfitting, we applied L2 regularization with an alpha of 0.005, which penalizes excessively large weights, ensuring better generalization to our new unseen data. Finally, we configured the model to run for about 2,000 iterations, with early stopping if no improvements were observed after 20 epochs, helping to save time and computational resources by halting training once the model stopped making significant progress. With this deep and carefully tuned model, we aim to capture more complex relationships with the data compared to our baseline models, potentially improving predictive performance.
Okay, so here are the results of our model in comparison to our baseline models. As stated before, we tested 5 baseline models: linear regression, decision tree, SVM, and a basic neural network, and gradient boosting. And each of these were evaluated by the 4 key metrics we discussed earlier. When we compare these models side by side, the performance of our custom MLP stands out clearly across every single metric. It achieved the lowest root mean square error at $23,850, which is significantly better than our next best at $34,000. Our average RMS across our 5 folds was also the lowest at around $32,000, confirming consistent generalization. And on top of that, our median absolute error was just $11,340, showing strong resistance against outliers compared to the other baseline models, particularly the neural network and SVM, which had much higher values. Finally, our model had also the lowest relative error at only 13.18%, outperforming all baselines, which range from around 18 to 47%. These results show that our tuned MLP is not only accurate, but also generalizes and handles edge cases better than any of the traditional models that we tested. Um, in terms of our group's prior experience, I'm dealing with prior experience. I've previously completed multiple projects and write ups on housing prices across the US as part of my MBA coursework at NC State. That background has really helped guide our data interpretation and informed how we approach this analysis from both a technical and business perspective. Thank you very much for your time.